Welcome to this presentation. My name is Diederick Vermetten, and on behalf of Niki van Stijn and Martijn Halsema, I will be convincing you to never use Raven Roost Optimization. If you're in this workshop, you might be familiar with the fact that metaphors can be quite useful to explain your algorithm. Algorithms like the particle swarm optimization are quite easy to follow because they are inspired by behavior of birds originally. And this shows you that thinking about some complex operation in terms of natural phenomena can help new people get insight into what different algorithms are actually doing. But as soon as you get past that initial stage, you might find that algorithms are also able to obscure algorithmic ideas. So thinking about a bird flying to a certain location has some relation to what's happening in a particle swarm optimization, but it doesn't quite capture the real story of what the mathematical operators are doing all the time. And this is the case in many of the algorithms that are being proposed all the time. So there are hundreds of these, ranging from hogs to plants to squirrels to even non-natural things like the mind-blast algorithms, etc., etc. So this can be seen as quite a problem. We have all of these metaphor-based algorithms, and we just cannot really see the forest for the trees. So there are many algorithms that are just flat out clones of other ones. They are just a different version of a particle swarm optimization that is not really contributing anything novel in the first place. And you can prove this equivalency on a case-by-case basis. But it's quite hard to do for all of them, so we just have to pick and choose which ones we use. And what we thought is, let's try to give this kind of projects to a bachelor student and see what comes out of it. So today's presentation is the result of a pilot project that we started with a bachelor student to see whether we could get them to understand these algorithms and show whether they contain anything useful or not. The algorithm we are looking at today is the Raven Roost Optimization. It's a population-based algorithm in a similar sense to a particle swarm optimizer, where we have particles that are going to fly through the space, with the additional change that the particles do not only move, they also have something that is called a perception mechanism. That means that while they are moving, they can observe points in some kind of radius from them, randomly picked. So the ravens all start from a common roost and then move towards some kind of new position that is either near the global best or near their personal best. And during this traversal, they can observe a few points within some radius around them. And the search can also terminate early if the raven finds a better solution. That's the core idea of the algorithm. So we have a population of ravens. They are flying from some kind of common starting point towards either a personal or a global best, or a region nearby that. And on the way to that point, they stop several times to observe something in some radius around them. We start our analysis of this Raven algorithm by looking at this roosting component, which means that each individual starts from a fixed point in space, or the common roost area. And as you can imagine, if all of our individuals start from the same starting point, then that creates a highly biased search in the beginning. because we will be much more likely to evaluate points that are somewhat near this roost than points that are far away. And this gets even worse by the fact that this roost is never updated in the search. So if we have an unlucky start, there's no chance to escape this, and we will just waste a lot of evaluations near where we place this initial point. So to illustrate this, we have a visualization of the search behavior of a sphere function in this case, where we have in red the random positions that the particles, the ravens, start out going towards. And we have in black the location of the roost. And then the colored points are the points that after the first iteration the ravens have visited, with the points getting so close together that you cannot really even see that they are points anymore. But we see we're only really evaluating a small region of the space in total. And luckily for us, this is a sphere function, so we are evaluating the region where the optimum is. But if we look at a different kind of function, then we see we had a roost starting in a very poor location, so we have evaluated a lot of very bad solutions before we eventually get somewhere near the better regions of the space that we evaluate very rarely. So this creates a highly biased search procedure. And the second component that we are looking at is this individual perception. So the claim of this this modification is that sampling around parts of this trajectory will improve the algorithm. Instead of just going to a position I'm about to go to, I stop several times on the way and I look in some kind of radius around me. And that does work in their paper. They show that with this enabled, we do gain quite a bit. But if you then look at why it is that you gain quite a bit, it is because the way that you define the notion of a generation. The comparisons that were done with this Raven roosting algorithm, and with many of the algorithms like it, are done on an iteration basis. And if you add this perception, you can see that still as one iteration of the algorithm. You just have multiple evaluations per individual per generation. And that again highlights the importance of a fair comparison. Comparing based on function evaluations versus comparing based on iterations of your algorithm, because you can put as many evaluations into a generation as you want. And then you can have nice plots on a per iteration basis showing that you do beat something like a particle swarm optimization. We have similar problems with their implementation of the stopping mechanism, which we will not go into now. Another aspect that I want to touch on is the way that this scales with dimensionality. And you might think from the roosting that obviously doesn't really scale with dimensionality, because you start from a fixed point that as soon as you increase dimensionality beyond something like 2, you start to really limit what parts of the space you are covering. But also the perception and the sampling around regions of the global best is something that is fixed, a fixed size radius, and there's no really way that this scales, which some other people have also noticed, and they created an improved Raven Roost Optimization algorithm that they claim scales better by modifying the stopping criterion and by modifying the way that we select whether we go towards the personal best or the global best based on how good this personal best is, instead of doing it at random. And as we will see a bit later, this change does not really do anything to help this algorithm become any better. So let's get to actually the algorithm itself. There were quite a few ambiguities towards implementing this algorithm properly that had to be overcome to get to a functional code. But in the end, we translated the metaphor-heavy description into this pseudocode, where we have first this roosting component, so it's a uniform point in our space. We initialize the personal best for each raven individually. Then we have this choice between going towards the global best, or some kind of where we go towards a location in a radius around the global best solution, or whether we go towards our personal best solution. And then we have this individual perception part, where once we have chosen the target, we take several steps towards that, and at every step we evaluate some point within, again, some kind of radius. And then we have this update of the personal best, and if we update our personal best, then we can have this stopping condition. So we can potentially stop once we have improved our solution. This is the whole pseudocode. There are some parts of some bookkeeping, but these are the important components. So we have roosting, we have choosing to go towards global or personal best, the individual perception, just sampling along that line to that target, and potential early stopping. So this we translate into code, and we can then go to benchmarking. So we compare our algorithm to random search and to a basic particle swarm optimizer. And of course we have several versions of this Raven Roost, because a few different versions are tried in these papers, including the improved Raven Roost. And the only plot I want to show you is this, which is an aggregated cumulative distribution function over 24 BBOB problems, where we see in orange PSO doing okay, and in yellow random search, and all of the Raven Roost algorithms are either worse or equivalent to random search, even with budgets of 10,000 evaluations. So it really does not perform well. So this should in its own be reason enough to not use it. But for completeness, we will also compare briefly to the particle swarm optimization from a more foundational perspective. The main changes that this has relative to a normal PSO is that we start from the same position, which, as we mentioned before, just creates a strong bias. There's no evidence that this helps the search. We have a stronger difference between following either personal or global best. And in particle swarm, we go towards some kind of weighted combination of personal and global, while here we go either towards one or the other. And that's a modification that might make sense, but it's also something that already was discussed in the original PSO paper as a logical way to modify this algorithm, so it's not doing anything new. And they have this random perception component, which you might consider as novel, but it's really just adding more samples along the way to a target, which doesn't really seem to help much if we are doing the evaluation fairly. So with this in mind, with leaving out a few of the details you can find in our paper, there's relatively few steps needed to transfer this Raven Roost optimization to a slight modification of canonical particle swarms. Lessons we can draw from this, and the first and main one is that we need to really use proper standards for empirical comparisons of algorithms. It's very easy to miss differences in amount of evaluations between iterations and things like this, and so at the very least code should be made available so we can verify these things later on and be sure that we have the right interpretation of what is written there. But this kind of burden of showing that you're doing something new is not something that should come from reviewers or people like this only. It should really come from the people proposing the algorithm. It's on the people making a new algorithm to really compare it fairly and to show what they're doing is really something new and something that should be used to advance the state of the art rather than copying something that is already out there. Wrap this up. Of course, as the title already said, do not use Raven Roost Optimization. And in general, it's probably best to avoid many of these novel metaphor-based algorithms that hide behind their flowery language and focus on algorithms that have really precise mathematical descriptions that are explored well and that have been adopted by the wider community. So let's not try to invent another 100 wheels and just say we modified the ones that we have to fit our purpose instead of making new ones.